Good evening, everyone. I welcome you all to the this last wrap-up session for NPTEL course Energy Conservation and Waste Heat Recovery. So, as of yesterday, we have covered all the 12-week classes. So today, this is the extra session. In this, we are going to wrap up our course and we are going to revise like our previous assignment questions because your exam is about to come. So maybe this revision will help you. In this, we will go through like little bit from all the concepts from week 1 to week 12. So I try to cover most of the like conceptual assignment questions and let you know the concepts. And if you have any doubts, so you can ask them. So maybe we can wait for you can say 5 minutes. After that, we will start. Hello, Prashant. How are you? Prashant, can you hear me?
Hello.
Yeah, can you hear me? Am I audible, Prashant?
Yes, sir.
Okay, okay. And my screen is also visible. Everything is fine.
Yes.
Okay. I think you were also present in yesterday's class, I think.
Yes, sir. Yes, sir.
Okay. And one of like you were two there. I think one of your friend was also there.
One was there, sir. Actually, not means knowing to him, sir, but I
Okay,
know.
okay, okay, okay.
And
So yeah. I think then there were three actually because in last class there were two batchmates. I think yeah.
yes,
Okay, okay. So we will wait 1 more minute and after that we will start.
sir.
So basically, as you know from yesterday's class, we have already covered all the 12-week classes. So today just we are going to go through all our previous assignment questions. So
Sir.
because in this way, we are going to touch all the concepts from week 1 to week 12. So I will try to cover almost every concept and every question from our previous weeks. So let's see how far we can go.
Sir.
So Prashant, how many classes have you attended as of now?
Sir, no, not more than 6 to 7, because, sir, due
Okay.
to time constraint, actually, I recorded session. I already getting in touch with that, but the live session, due to some constraint and some official work and time clashes, whenever and what amount means I can devote. I've tried my best to get it.
Okay. Okay.
Uh,
Yeah. Nice. Nice. So maybe we can start because this is final class, so maybe you can share your thoughts.
So, uh,
Yeah, about this course, how this course is going to help you, and like what did you learn in this course, and like what are the like best points about this course, and anything you want to say. Yeah.
So regarding that, the means last session, which the project analysis and that NPV, it will be, really be, benefited in a project calculation, project the cost and cost benefit analysis. But sir, the point is that whatever I get it from the class and what I can apply in my factory, in my organization, some gap is there because whatever is a uh, means concept is a though it is a theoretical, it will be beneficial in getting the work done. But sir, somehow some gap is there. I thought I think means because sir in my factory I am working in a defense department where a production
Okay.
means ammunition and all that. There are very
Okay.
many means air conditioning project there heat but there is no heat recovery system is installed in my factory. That is a many scope, but cost is one of the factor which may constrain in doing so. So
Yeah. Yeah.
means from what and how I should start to get the practically implement this theoretical knowledge which I get from these classes. So I'm not getting exactly the means. So that is the area, that is from where I should start. There is some
Okay.
difficulties.
Yeah,
So because
actually, the meaning of this course is that now in this course we have covered different kind of technologies, different kind of mechanisms that you can apply to recover waste heat. Okay,
yes, sir.
so now now as you said that you are having a system and you are not having any kind of such systems for waste
Yes,
heat recovery.
yes,
So
sir.
first of all, your approach in my opinion, first of all, you have to understand like what kind of system like you are having, and like what are the points there is heat is like wasting actually. First, you have to identify those points. You have to identify the state of those points, like what is the temperature there, what is the pressure there, okay, what is the flow rate of the waste stream. So first of all, you have to identify all the points for your existing plant. When you will have all the points, note that points down, okay, then based on that points you have, like in this course we have covered different kind of technologies. So you have to see that these parameters like this pressure, this temperature, this flow rate, so and cost also. So you have to identify like this kind of technology can be beneficial for this type of state conditions, and this is also in our budget. So you have to do that actually. Sometime because when we are like talking about waste heat recovery, so initially it can be costly, but you have to find a plan, like that if we are installing this technology, then you have to present the benefits of that. So you have to justify that if we are installing the waste heat recovery, so we are getting more efficiency, we are getting less emission, okay. So maybe you can draft a plan, you can present that plan to your superiors, and maybe they can approve the technology. So I think this should be your approach. So now you are aware of all the available technology in the market, okay, theoretically. Also, we have, I think professors have also given very good examples of these technologies. So maybe you can also relate to them. You can ask, you can discuss the efficiency. You can also like Google it, like what kind of technology and what kind of more practical examples are also there. So you can find them. You can do some literature review also regarding the technology. But the first thing, the main thing, you have to thoroughly analyze your system, your current system. Okay. And first of all, you have to do like, how can you minimize the waste heat in the current system? That is the main point. And you should know about all the parameters of that. That should be the start point, and after that you can apply this knowledge, I think.
Sir.
Yeah. So what kind of system like you are having in your factory?
Sir, basically we are having around 70 to 80 air conditioning system, means centralized air conditioning system, means
Okay.
sorry, it's decentralized. So,
Okay.
and there are very old type of technology, that is a VCR, vapor compression refrigeration system. Uh,
Okay.
and boilers are also there, 40 to 15 boilers, compressors are there, chilling units are there, and ice producing one unit is there. So, but the
Okay.
area is very large, around 7 to 8,000 acre areas. So,
Okay.
it is a defense particular, and there is some guideline, that is a safety guideline to install that building. That's explosive building, the minimum distance
Okay.
and that. So
Mm-hmm.
basically, there are means of big scope to get the heat recovery, to get that waste heat from west, and can utilize. But sir, distance is also one of the factor, that if you want to utilize that, but the other factor, that is of cost, will become a more dominant over that recovery. I think that.
Yeah, yeah, yeah. That can be a point. That can be a point. So, uh, that's engineers do actually. You have to find a solution because we know there are many constraint also, but yes, still you have to find like some you can say jugaad. Okay,
Yes, sir.
so you have to come. You like you are in R&D department or in which department you are working in project department?
Sir, actually, I'm in a not on project. I'm actually, my duties variable, means rotation basis. Actually, I'm now in procurement. That procurement
Okay,
of that.
okay,
But for some time, I was in production, in maintenance. So that is a shift going to change, not a fix for a long time. So 3 to 4 years
okay.
usually go. The duty can be changed. So that
Okay,
is a.
okay. So maybe you can maybe if you are saying that this kind of building is there, then there will be a separate department for this kind of handling all the equipment and machineries.
Yes,
So
sir. Yes.
maybe yeah, maybe you can meet with them. You can have a joint meetings regularly, and maybe you can discuss your knowledge with them. So maybe actually discussion is a very good thing. So you should brainstorm, and maybe you can visit with them to these units, and you all can find some solution because now you have knowledge about waste heat recovery. You know
Yes.
things like this kind of things are possible actually, because if you are saying that there are boilers, okay, so boilers need heat, we know that. So you are generating the steam, and also maybe you can reduce the load on boiler by utilizing the waste heat to generate the steam by applying some more heat exchangers there. Just uh, like with some heat exchangers, maybe you can find some way to decrease the heat load on boiler. That can be like just I have not seen a system, but if you are saying that there are boilers and all, so you can maybe try with this also. So think about it, and maybe some other ways are also when you are physically there, you have to find those ways. So you can discuss with them, with your colleagues that they are handling the systems. Then maybe there can be solution. But because as the waste heat recovery is today's demand actually, because we can see that there is the whole world is concerning about the pollution, the CO2 emission, and India is also doing a very good in this actually. So the current government is like doing many steps to reduce the CO2 emission, or like also pushing the hydrogen economy, also pushing the biogas and CBG and all. So maybe if you come with, you are working in a government sector, so if
Yes,
you come with a solution that can reduce the pollution, that can reduce the carbon emission, that can reduce the load on the system, so maybe they will approve it. So you have to come up with a good plan, good solution, good technology, and you can apply that.
sir, sir.
Yeah. Okay. So any more thoughts about this course and project? Any more thoughts you want to share?
Uh, Not sure, sir. But I definitely, if I get some idea, I can share through the mail or some other mode.
Yeah, yeah, sure, sure. So I think you are like working professional. So what was the motive to join this course? Only to to understand the waste heat recovery, or like it was in your? protocol or like something?
No, sir. That not protocol. It's my interest to get some information, updates, and
Okay,
technology.
okay.
What are emerging technology in this field? So that is my
And you
one
are
of the
from mechanical background or electrical?
mechanical, sir.
Mechanical, and you have your master's degree or bachelor's degree?
Sir, master degree, thermal. Actually, I'm thermal engineering
Oh, from where?
from IIT Bombay, sir.
Oh, nice, nice. In which year?
Sir, 2013, sir. Pass out from 13. Around
13.
10 years.
So you are having a very good experience, I think. Yeah, 13 pass out. So you are having very good experience. So from
Yes, sir.
that after masters, you are in the same company or like you have changed it?
No, same company, sir. After that, I joined as I'm joined as a UPSC engineering service exam as a group officer, and
Okay,
currently the
IES. I think you are IES. I think, yeah. Then
yes,
yeah. Okay, okay. So yeah, actually you are also having a very good position. So now you are at like actually you are a policy maker now. I think so because you are having a good experience. You are a good position. Then you should apply it because India
yes.
needs it actually. Yeah.
Yeah, my motive is only that, but sir, some constraint. That constraint I told na that the cost and second that means one of the that is a key parameter or key factor to in obstruction the doing that implementation is a cost. So
Cost
the
actually initially the cost will be high, but you have to show them that if today we are in like as we yesterday also we discussed time value of money. So you have to show
yes, sir.
them that we are investing today. So but like now the carbon credits are also there. So they are also coming in picture. So you have to show them benefits actually. If we are investing, but in this way we are reducing the pollution
Yes.
and what will be the saving in future. So like suppose if you are putting some money today, maybe that money will can be recover in 5 or 10 years,
In the
but the
yes,
benefit will be for 30 years. So that things you have to present them actually. You are on a good position. I think you can
sir.
do this. So please utilize this knowledge.
Sure,
And
sure.
yeah. Try to implement something good because in government sector, we need many improvements in our companies. Yeah, because
Yes,
I
sir.
was also in HPCL. Just my
Oh,
experience. I was there for a field engineer for 3 years. So there also
oh,
like just a simple example. Actually, there are pipelines. So pipelines we used to give some trackers to our line workers. So because
mm,
there was a pipeline of 90 kilometer.
yes,
So there are some security guards. They are like going daily, morning and night to
sir.
to cover the pipeline, so that there will be no man like no one is like tapping on the pipelines, tapping off the pipelines uh, to do something like what you can say. Actually, there are many gangs actually. So they tap off the pressurized pipelines
Sure.
and they
For sir.
yeah. They're doing some leakage from that and they are filling their tankers actually. So
I
in
got.
many areas, these kind of
Mm,
things are going on. So we used
yes.
to send our security guards there. So we are going. Normally, we give them like a small device in which you can
Mm,
put a SIM card, so that
mm.
we can track their location. Just a
Yes,
GPS device, you can say.
right.
So yeah. So when I observed there, actually, so we were using some particular telecom sector. Okay, so there was a common plan there. So that plan was having, I think, 4 GB of data, 4 GB of data per month, and I think around uh, 500 minutes and all. But they cannot call from them actually. They just have to connect to the control room's number, and they just need only a little bit of internet. They don't need 4 GB of data. So that
Okay.
plan was around costing around, I think, 900 rupees per month for one SIM.
One
And we
sim.
were
Okay.
using, yeah, we were using around 100 of SIMs. So yeah, there was also a small plan of just 125 rupees.
Mhm.
So yeah, so I found that point, and just I changed all the plans to that 125 rupees plan. So directly you can
Really?
say from 900 directly to we came to the 125 rupees, and that was only on one location.
Yes, yes.
So you can see the pipelines are everywhere. So the small things we have to just look into it, because uh, just we have to like look carefully and we can save a lot actually. Yeah.
Yes, yes. That is a good example, sir.
Yeah. So just look carefully and you are at good position so you can implement things actually. So I think you should use this knowledge and try to implement it. Yeah.
Sure, sir, sure.
Yeah. Okay. Thank you for sharing your thoughts. So let's just quickly go through all the past question. So it will be today. I think we will go little bit fast because we have to cover a lot. So just like going through some examples and directly we came to the solutions. Okay, just we will discuss some things. Okay, so like this question was the about like most suitable for waste heat recovery in a plant with an unavoidable generation of waste heat. So this was the question. So the best thing that like we will also discussing that to what should we do. So first of all, whenever we want to apply the waste heat recovery, so the answer should be the adoption of waste heat recovery principle at the design stage of the plant. That will be the good option. Then retrofitting waste heat recovery techniques in an existing plant. So the second point I think will be for you. So retrofitting, so waste heat recovery techniques in an existing plant. So you are having a plant, you already have a plant, you have to find out all the points, then you have to retrofit it. So these two things are very important for a waste heat recovery plant. Now the utilizing waste heat recovery one can generate. So if you are having waste heat recovery system, so we can directly electric power directly, electric power indirectly, mechanical power, heating and cooling. So we can do multiple things. So for this, first of all, you have to identify what kind of plant you are having and what are the points on those points. These are like waste streams available, what is the temperature, pressure, and what are the condition, and what will be the effect of if you are tapping of some waste heat recovery there, then what will be the like effect of that stream on the other process also. So everything you have to analyze, but you can recover all these points like electric power, mechanical power, heating and cooling. So which of the followings are the reason for waste heat generation? So there are many regions like thermodynamic limitation of cycles. We know that we are limited by the Carnot cycles and all. Heat transfer limitations also there. Physical limitation of the equipment like sizing, length, etc. Material properties, etc. So plant layout is also important. Characteristics and chemical composition of exhaust stream. That is also important because you have to see the composition of the exhaust stream. Is it any having toxic element or not? You have to see that. So these are the points you have to look into it. Which of the following are source of waste heat? So the source of fossil fuel waste power plant, majorly, and the nuclear power plant, and the hot products in metallurgical process and chemical industries. Hydropower plant is completely renewable, so that is not a source of waste heat. Okay. Now the correct statement regarding the forms of energy. So heat and work are forms of energy in transit. Choose the correct statements. So the correct statement is all stored forms of energy are point function and properties of these are the basics of this thermodynamics. So just move a little bit forward fast from here. So consider the two statement for the first of thermodynamics. So the C, the first is applicable for a cycle. So for a cycle, this is the first law. Delta Q is equals to delta W. The net heat added and rejected will be equal to the net work done. And the second is applicable for a single process. So this is an example of a like economizer. Okay, so just we have to follow like what is the input and what is the output. You have to do the enthalpy balance and all. You can find this. So the following statement are true. So the first law of thermodynamics relates to the quality of energy. So in first law, we'll say that the energy is conserved. Okay, it cannot be destroyed. Okay, so it's like relate to the quantity of energy. In second law, we talk about entropy, we talk about the quality of energy. Like heat is, if you are saying that there is a around 100 kilowatt of heat available, but that heat is not will not generate 100 kilowatt of work actually. Okay, so you have to see the exergy, that how much of that heat will be actually able to generate the work. So here we will see the quality, because when you use that heat to generate the work, actual work, then due to the entropy, most of it will waste out. Okay, so maybe from 100 kilowatt you will be only able to get 20 kilowatt or even less. Maybe it depends on the like many parameters actually, what is the process and all. So exergy is very important. So always, like if you are doing like, if you want to find the efficiency of a plant, so you should go for exergy efficiency, not for the energy efficiency, because the exergy efficiency will only tell you the exact details about the plant. Okay, because the exergy destruction is very important. So try to find the exergy efficiency data for your plant, because energy efficiency will not give you the correct data. The exergy efficiency is very important. So which of the followings are corollary of the second law of thermodynamics? So first, second, third, fourth, and fifth, all. The direction of the process, concept of irreversibility, concept of entropy, and all. Okay. So these kind of numericals maybe can come to your exam also. So heat is transferred to a heat engine from a furnace. Okay, at 80 megawatt. If the rate of waste rejection is nearby is 50 megawatt, determine the net power output and thermal efficiency of the heat engine. So whenever you find a like any numerical like this, so the first thing you should do to try to draw a basic schematic. Okay, so in this you can mention like a T1, T2, and heat engine. Okay, and the mark the like heat flows and the work done. So when you will do this, then I think you can remember like what you have to do with the only data. Sometimes it get like confusing, so uh, try to always follow this approach. Draw a basic schematic, mark all the points, mark all the temperature, then apply the formulas. So here you can apply like T1 furnace, T2 the river, then heat engine, then it's like developing some work. Okay, this is the Q1, this is the Q2, T1 is greater than T2. Okay, so now the net rate of work output will be Q1 minus Q2. So now you know the Q1 we have given 80 megawatt, Q2 we have given 50 megawatt. So 30 megawatt will be the work output. So the efficiency is net work output upon rate of heat supplied. So now you know the work output, you know the heat supplied, that is Q1. So W upon Q1, it's going to be 37.5%. Okay. So in this way, you can find the answer. Again, another question. So in this also, we will follow the same approach. Just draw a diagram. Okay. House at 20 degree, outdoor is -2. Okay, and like heat pump, so we have to provide the work here. So COP is the desired effect upon work input. So so your desired effect is the house. Okay, QH. So the QH upon W. So after this, you have given some data here. You have given the COP. Okay, you have given the heat. Just put this data. You can find the work required. So this thing is important. Schematic is very important. Try to follow this approach. Again, numerical, you have given a schematic, just you have to find the temperature. Okay, so just apply the formulas. So this thing is very important in this kind of question. So move it. Okay, this is like the correct statement. So all of the above. So this statement is very important. Like COP of heat pump is always greater than COP of refrigerator. 1 plus COP of refrigerator. So COP of heat pump, like, so this will be the desired effect upon work input. Okay, so the correct answer is all of the above. again like similar question. So in this we have given efficiency, and the important thing is that whenever you have temperature in degree centigrade, okay, and when do you apply this formula, always put the temperature in Kelvin. So this thing is important, otherwise you will get wrong answer. So just convert the temperature in Kelvin, then put in this formula. Okay. So this is important. Temperature should be in Kelvin. So what are the possible cause of waste heat generation? So yeah, the economy and energy policies, physical limitation, and minimum allowable temperature of cooling. So these are the important points for the waste heat generation. So major source of waste heat, coal-based power plant and oil refineries. So these are also coal-based plant because the major source, like where are we having like combustion, and like we are burning something like in boilers and all. So there will be waste heat because the heat, the you can say the heat is major source of wasting the energy actually. Whenever we are burning something, it's going to be waste, like because you know the the conventional cook stoves, that those we are using in villages actually, and like we are burning wood, then they are only having efficiency around 10%. So basically 90% of energy is wasting. Okay, so we are having only 10% of efficiency from the very conventional cook stoves. So now in market there many of designs are available. We are like doing something in IIT Delhi also. Many of my colleagues are also developing some new design cook stoves so that they can increase the efficiency of that cook stove like up to 20 or 30%. So that's a actually very important thing. So that's why actually fuel cells comes into picture, because in fuel cells there is no combustion, and there is no combustion, so we are not limited by the Carnot efficiency. We are not limited by the like limitation of the efficiency. Okay, so we can directly convert the chemical energy into electrical energy. Okay, as of now, what are we doing actually? We are burning the chemicals to generate the heat. Okay, or we are burning the chemicals to convert that energy to into mechanical energy, and from mechanical energy we are converting that into electrical energy. So with fuel cells, we are eliminating one complete process. That's why efficiency is very high. So maybe I hope in future this coal-based power plant will be replaced by the solid oxide fuel cell plants in future. Yeah. Oil refineries. So these are the major source of waste heat. So waste heat recovery helps in, so it's saving both running and capital cost of the plant. So if your plant is already installed, then it cannot change the capital cost, but running cost can be reduced in long term. Okay, in short term, you have to invest something to install a new system for waste heat recovery. But if you see in the long term, then there will be saving for sure. For a cyclic process, change of thermodynamic property is, so it's always zero. Which one is the correct statement regarding waste heat recovery? So both quality and quantity of waste heat are important. So you should know the quality and quantity. Okay, quality means
Sir,
like what?
yes.
Yeah, Prashant. Yeah.
Quality means temperature only, or sir, pressure and all. That's
Actually, yeah. Quantity means like what is the waste stream like flow rate basically. Like what is the quantity of flow rate? The quality is the temperature, you can say also temperature. Okay, because if your waste stream is available at 800 degrees centigrade, okay, and maybe the
yes.
flow rate is low, but that is having more energy, so that is the quality actually. Because uh, uh, for to understand more about quality, I think you should cover the exergy. Okay, so there
Mm.
is a Moron Shapiro book, a good thermodynamics books. Maybe you are you aware of this book maybe. So please try to
Yes.
cover the exergy chapter.
Sir.
Okay. Yeah. So whenever you are considering anything, so try to find the exergy efficiency of your plant. Okay. Yeah. Yeah.
Yes.
So there, yeah. So try to do the exergy efficiency, and maybe your current plant is also using some kind of thermodynamic software or not, I don't know. But if they are using, so or maybe you can hire some like consultant, so they can do the complete modeling of your current system actually. Because if you
Sir.
have your current systems modeled in any thermo software, so that you can easily change some parameters, that will be quite very convenient actually. So you can hire maybe in your department also, in any maybe you have some in R&D, you are having some engineers, they can do modeling for you. There are many different kind of commercial software available nowadays. So you're like you were saying that you are having some chilling units, some boilers and all, so they can do
Yes.
complete modeling of your system. Okay. Actually myself, I am also doing modeling in my, that's my PhD topic actually. I'm doing a complete power plant modeling for solid oxide fuel cell systems. Okay. So you
Sir.
can hire
Sir. Sir.
somebody to do the complete modeling. After that, you can do, now you have actual parameter for your system. Okay. So those parameter you will put in that model. Based on that, you will find the energy efficiency and exergy efficiency. Okay. From that
Sir.
model, you can find out like this component is not good actually. Because suppose if you are using a component that is around 10 or 20 10-year old, okay, so that 10-year-old heat exchanger, maybe it's worn out and all, so there is so much exergy losses in that equipment, and that equipment
Sir.
cost maybe around only 10 lakh rupees. But you are having, if you count the loss, maybe in next 5 years, if you use the same equipment, that loss will be more than 15 lakh. So it's good to replace that equipment now actually, because if you replace that
Sir.
equipment, maybe you can save up to 20 lakh. So that's important actually. So the first thing I think you should, uh, you're like you are having a big plan, so try to complete a small thermodynamic model system of your plant in computer actually. So with that, you can tweak with the input and output parameters. With that, you can find out like where is the maximum exergy destruction or quality destruction is happening. Maybe you can replace those equipment. So that can be also the first approach of your modification of your plant.
Sir. Sir.
Because
Sure.
because physically we cannot change anything directly. We should have some backup also, we should have some reasoning, so that model can help you.
Okay. The service can be hired, sir, for that.
Yeah, you can hire, there are many companies, there are many startups and companies, they are doing this kind of thermal modeling actually. Yeah. So
Sir.
they can, if your plant, they can do the complete modeling. I think there is a good software, common software, I don't know the name. Thermoflow, I think the software is there. Thermoflow, like, or Thermex flow, like this. So there are many software. I am using Cycle Tempo, that you can actually, you can also try with yourself. It's available in demo version also. So in Cycle Tempo, you can do this kind of boiler and this kind of heat exchanger modeling easily.
Okay, sir. Sure.
Yeah. So the quality means basically like what is the quality of that heat? Like you can say the exergy actually. Like
Yes.
uh, quality means if the temperature is very high, it means that is a good quality. Okay. Mean there will be very less entropy. Quality
Yes.
high means very less
Entropy less,
entropy destruction is there. Yeah. Yeah. So mean there will be more exergy available.
sir.
So heat and work are basically path functions. Okay. So they are
Yes.
not point function and intensive properties and extensive properties. They are path function. The first law of thermodynamics, U1 to U2 minus U1 plus W2 minus W1. So which statements are true for second law of thermodynamics? So it describes the direction of heat flow. Okay. And it introduced the concept of irreversibility. So irreversibility, that is very important. Okay. with the life of equipment, actually irreversibility increases. If irreversibility increases, okay, then the efficiency decreases.
And there is a scope then it waste heat.
Yeah. More irreversibility means there is more waste heat.
Yeah.
Okay. So you have to find out like which equipment is there is maximum exergy destruction. So the main thing you can do, like suppose there is a equipment, just quick thing maybe you can do. Okay, so just read the input properties and after the equipment output properties and what is the result from that equipment. With these three data, you can easily have from your plant. So just compare the energy at this point, energy at this point, and at this point. Maybe you can find how much energy is destroying in this equipment, like how much loss is there of energy. So you can find this. The COP, so it's Q2 upon Q minus Q2, okay. But by waste heat recovery, one can generate thermal energy of high quality. So these are the like possible benefits. If you are having waste heat available, you can generate electrical power, you can generate thermal energy of higher quality. You can also do heating and cooling. So these are small numericals. So these you can easily do with the simply the first of thermodynamics and all. The Carnot cycle consists of two reversible adiabatic and two
Yes, sir.
isothermal processes. So which of the following are cause of irreversibility? So the irreversibility can be due to the friction, due to the viscosity, to the mixing, free expansion, and heat transfer across the finite temperature difference. So these are the reasons for irreversibility. Okay. So as the life of any equipment increases, the friction between the parts will increase. So it will cause more irreversibility. The closest statement is del Q by T from less than equal to 0. So this is the TS diagram. Okay. So the correct statement for TS diagram. So area 1265, area 1265 represents the heat added to cycle. So this is the heat addition process. Okay. So the area under this curve will be heat added to the cycle. Similarly, the area 4365, 4365. So this area will represent the heat rejected by the cycle and the area between this. Okay.
Work.
It will represent the work done. So you can see here. So the below area is actually waste heat. This is your waste heat because initially you have added this much of heat, but you are only getting output of this heat. So this heat is wasted actually. So now you have to apply some technology so that you can recover as much as possible from this heat. So in this way, you can increase the efficiency, you can utilize the waste heat recovery and do like do good to the environment. Okay. So this is the our scope actually. We are getting it. This we are adding. So this we can recover. So here we have a like heat engine between two reservoirs. Okay. Temperature are given. The heat engine draws 500 kilojoule from the high temperature reservoir, rejects to the low temperature. What is the maximum work? So maximum work means you have to apply the Carnot formula. Okay. So the maximum work will be the efficiency of Carnot multiplied by the heat added. Okay. So the efficiency will be 1 minus T lower upon T higher. So again point temperature should be always in Kelvin, okay, multiplied with the heat added, you'll find the maximum work done. Again, the same kind of question. So here we are like dealing with the entropy, okay. So entropy generation is the measure of irreversibility of a process. So as high as the entropy, then it means that the process is more irreversible. The entropy balance of heat transfer to the reservoir rate. So generation will be source plus sink. So delta S is Q by T. So put the data, find the entropy. Again, the heat transfer to the reservoir will be, this will be the entropy generation. So during a reversible process from 1 to 2, the change of entropy, it will be equal to del Q by T, 1 to 2, reversible. So an adiabatic vessel contains 2.5 kg of water at 20 degrees centigrade. With pedal wheel, the work transfer, the temperature of water is increased by to 30 degree. If the specific heat of water is assumed to be constant at 4.187 kilojoule per kg Kelvin, the entropy change of the universe is. So whenever you are dealing with entropy change of universe, then entropy change of system plus surrounding. So the system will be mc ln T2 upon T1. You have T2, you have T1, put the data, and this will be the entropy generation for the universe. So consider the entropy balance equation for a process as given below. So here delta S generation is 0 for all reversible process. If your process is reversible, it means there is no entropy generation will be there, because the both initial and final condition can be again regained. So if there is entropy generation, mean there will be some losses, then the process cannot be reversible, because if there is some losses, then you cannot come back from you cannot come back from your the final state to the initial state. And delta S is a measure of irreversibility of process, so it's a measure of irreversibility. Del Q by T is 0 for an adiabatic process. Okay, it is 0 for an adiabatic process, and del Q by T and S generation are 0 for a reversible adiabatic process. So these are 0 for reversible adiabatic process. So a frictionless piston cylinder device contains saturated liquid vapor mixture of water at 100 degree. So you have given temperature, water, it's a constant pressure process. Okay, 600 kilojoule of heat is transferred to the surrounding air. So this much of heat is transferred to surrounding air. Surrounding temperature is 25 degrees centigrade. As a result, part of water vapor contained in the cylinder condenses. So due to this heat transfer, the part of vapor will be condensed. Okay. Total entropy generation in kilojoule per Kelvin during the heat transfer process. So write entropy balance equation. Entropy generation equal to net entropy transfer by heat plus change in entropy of system. So del Q by T system plus del Q by TB. So put the data, and this will be the answer. Entropy transfer is due to its mass and heat transfer. So entropy transfer is due to the mass and the heat transfer. So which of the following statements these are correct, or like given the first law efficiency or second law efficiency and the Carnot efficiency? Okay. So the second law efficiency is efficiency of Carnot efficiency, sorry, first law efficiency upon Carnot efficiency, or Carnot efficiency can be the first law efficiency upon the second law efficiency. Which of the following is true? So for work producing devices, second efficiency equal to useful work upon reversible work. And for work absorbing device, second efficiency will be reversible work upon useful work. So both statements are correct. An electric resistance heater for residential building is claimed to have an efficiency of 100%. So assuming an indoor temperature, you have given outdoor temperature, second efficiency of the heater will be. So the second efficiency of the heater is given by the COP of heat pump and COP of heat pump in reversible. Okay. So it is claimed that the heater converts the total electric work supplied into heat. So the COP of heat pump will be equal to 1. So COP of heat pump reversible is given by, so it will be 1 upon 1 minus TL upon TH. It will get 26.7. So the second efficiency will be COP of heat pump upon the heat pump reversible. So it will be 0.037 to 3.7%. So the waste heat stream in a process industry, we have given 250 kilowatt capacity is available at 400 degrees centigrade. The ambient temperature is 27 degrees centigrade. The exergy of the waste heat is. So the exergy of waste heat is Q 1 minus T naught upon T1. So 250 1 minus T naught upon T1, so 138.55 kilowatt. So if you are having waste heat that is 250 kilowatt capacity, so you can convert only 138.5 kilowatt into work. Okay, this is the exergy of waste heat. Entropy is an extensive property. For a closed system undergoing an irreversible process, the entropy of system, so entropy system can increase, can decrease, and remain constant, depend on the process. So what is the correct statement, correct expression for system undergoing a reversible cycle? So it will be for a reversible cycle, del Q by T should be equal to 0. Quality of the waste heat. So it depends on both the temperature and chemical composition. So as much as high temperature is more, it means the quality is more. I think we have students online. Alok?
Yes, sir.
Hi. So I think you were also in yesterday's class?
Yes, sir.
Okay. So today, Alok, we are just covering the our previous week's assignments questions, okay? And we are trying to identify the main concepts. If you have any doubt, let me know. Okay. So the maximum useful work obtainable a system goes to dead state. So if dead state, then it means is the availability. Okay. The quality of energy utilization is determined by the second law efficiency with the help of entropy and all. The second law efficiency of a refrigerator is equal to, so refrigerator means work consuming device. Okay. So reversible upon actual. Okay. Because the reversible work will be the less work and actual work will be the more work, because actually there is no reversibility in the refrigerator. So the work input will be more. Availability of a system during a process, so it destroys due to irreversibility. Availability destroys due to the irreversibility in system. So figure of merit of a heat pump is always greater than 1, because the COP of heat pump is 1 plus COP of refrigerator, so it will be always greater than 1. The correct statement regarding irreversibility. So what are the correct statements? So the flow of heat from high temperature to the lower temperature can take place without any irreversibility. So yeah, from high temperature to you can go to easily to lower temperature. Okay. Irreversibility decreases the work done in a heat engine. So if there is any irreversibility, then there will be some losses. So it will decrease the work output from the heat engine. So correct option regarding the combined cycle for maximum efficiency. So the heat rejected by topping cycle is the heat supplied to bottoming cycle. That is the main point actually. In waste heat recovery, our main objective is to utilize the waste heat from topping cycle by placing a bottoming cycle. So bottoming cycle, we are not adding any extra heat. We are using the heat rejected from the topping cycle as an input to the bottoming cycle. So statement A is correct. The figure shown below is the TS diagram of a Rankine cycle. So this is a Rankine cycle. This is 1 to 2, 2, 3, 3, 4, and 4 to 1. 4 to 1 is heat addition, then expansion, then again condenser, then pumping. This is the Rankine cycle. Okay. The correct options for thermal efficiency of the cycle is, so it's C. The work output will be H1 minus H2, and the heat added, it will be H1 minus, sorry, not D, it's C. H1 minus H3. H1 minus H3, or actually it should be H4, but the H3 to H4 is a pump work, it is very less as compared to this. So we can directly use H1 to H3 if we have not given the data point for the enthalpy point 4. If you are having data for point 4, then you should do the calculation correctly. It should be H1 minus H4. But for approximate calculation, we can take heat addition as H1 to H3. So choose the correct statement related to the Rankine cycle. So it will be the B. Irreversibility causes an increase in pump work. Irreversibility causes a decrease in the turbine work, because if there is irreversibility, we will get less work. Due to irreversibility, we have to add more work. So pump work will increase, turbine work will decrease. The pinch point puts a restriction on the highest achievable temperature. Okay. The terminal temperature difference TTD points puts a restriction on the lowest achievable temperature. So these are the some statement related to the Rankine cycle. So refer to the TS diagram of Rankine cycle with reheat and match the following. So it will be answer B. Okay. So 1 to 2 is the expansion of high pressure turbine. Okay. 1 to 2 high pressure turbine. 3 to 4 low pressure turbine. 2 to 3 will be your again the reheating. 3 to 4 will be the expansion in low pressure turbine. Okay. 4 to 5 will be the cooling of the exhaust steam in condenser. This 4 to 5 in cooling. And 6 to 7, 6 to 1 will be, the 3, the heating of feed water in the economizer. Should be 1, 6 to 1. Which one of the following the correct order of fluid flow in a steam power plant? So the correct flow is steam turbine, then pump, then boiler, steam turbine, sorry, it will be economizer, evaporator, and superheater. This is the correct order of fluid flow in a steam power plant. First economizer, then evaporator, then superheater. The open feed water heater is direct contact heat exchanger. Okay, so in this, the both stream, the hot and cold, will be in direct contact and they will exchange the heat. The incorrect statement. So the use of feed water heater increase the work output of same energy input. This is not correct because use of feed water heater increases the thermal efficiency of the power plant. Okay. The incremental increase in thermal efficiency of the power plant by addition of feed water heater decreases. Okay. Choose the correct statements for reheating in Rankine cycle. So it has benefit of getting high quality steam at condenser inlet. Yeah, because if we are doing reheating, then you know that. Okay, this will be the, you can see the input to the condenser will be shifted towards right. Okay, so it means that you are getting high quality steam at the condenser inlet. It increases work output because we are using the high pressure turbine and low pressure turbine, so work output is also more. A numerical, you have given data points, you have given enthalpies. This kind of numerical can be also in your exam. Okay, so just see that carefully. So you have to calculate what will be the pump work. So you need to calculate the pump work. So pump, you have to see, identify the pump points. Okay, so the point 5 and 6 will be required for the pump work. Okay, so pump work should be given by WP or specific volume VP, P6 minus P5. So I identify the points. Okay, so V5 is the specific volume of fluid at condenser outlet. So this is the condenser outlet. So V5 will be at 10 kilopascal pressure. Okay, so we have given the specific volume of such liquid at 10 kilopascal is this much. So we know the V5. Okay, we have also given the pressures 15 megapascal and 10 kilopascal. So you have V5, you have P6, you have P5. Put the data, you know the answer. Okay, so always don't confuse to see the tables and all that. This question is very complicated. You can see with the solution, the answer is very simple. First, you should try to identify the points where you have to focus. So in this particular question, you just need to focus on point 5 and 6. So don't bother about other points. Okay, apply the basic formula, find out the specific volume, you have given the pressure and all, just apply the multiplication. The same problem, the previous one, what will be the total heat supplied? So heat supplied will be your H1 to H6, and you are also doing the reheating H3 to H2 and H1 to H6. So you are supplying heat in the boiler, heat in the reheating. So QS will be H1 minus H6 plus H3 minus H2. Then specific enthalpy at state 6 will be like this. You have pump work, you have at the enthalpy of 0.5. So with this, you can find enthalpy at 0.6. Okay. So if you know the enthalpy at 0.6, other points are given in the table. Just apply the formula. This one, you can have the data. So the same question, what will be thermal efficiency? Okay. So now you have your pump work and all, you have also the heat input. So the efficiency will be net work output upon heat supplied. Okay. So we have computed the total heat supplied in the problem 6. Let us calculate the network output. So it can be WT1, WT2 minus WP. So we have two pump work and the pump is consuming power, so it's subtracted. So W net H1 minus H2 plus H3 minus H4 minus WP. So the specific enthalpy at state 4 can be calculated as HF 10 kilopascal plus this is the quality, because you can see the point 4 note is on exactly not on the saturation curve. It's slightly inside the curve. Okay, so you have to use enthalpy 0.5, then the HFG enthalpy between the difference, and you have to use the quality of 0.4. You can see, apply the formula. H4 will be HF at the 10 kilopascal. That will be on saturation curve. Then X4, the quality of the point, that is 0.896. HFG of that pressure, this much. So the enthalpy at 0.4 will be this. Then W net will be H1 minus H2 plus H3 minus H4 minus WP. Okay, so you have this value. Now the enthalpy will be, sorry, the efficiency will be net work output upon total heat supplied. So you have work output, you have heat supplied, the efficiency will be 45%. So in adiabatic turbine, the steam expands steadily. The data is given in the figure. We've given the H1 V1, H2 V2. Okay. Note that the inlet and outlet of turbine air same datum. Datum is same, so the potential head is 0. To write the steady flow energy equation for expansion to the adiabatic turbine, so it will be H1 plus V1 square by 2 plus Q, because this is adiabatic, so that Q is 0, and W out plus H2 plus V2 square by 2. Okay, so work output will be H1 minus H2 plus V1 square minus V2 square by 2. Put the data. Always remember that whenever you are solving this kind of question, be careful with the units. Okay, because maybe sometime it will be in megajoule, this will be in kilojoule. Okay, maybe this can be in kilometer per second or like that. Okay, so always remember that whenever you are doing this kind of calculation, be consistent with the units. Units should be in all should be in same manner. So the back work ratio important. Back work ratio is pump work upon turbine work. So what is the back work ratio? It is the ratio between the pump work and turbine work. Just find out. You have given all the enthalpies at state points. You have given the graph. This is the turbine work. This is the pump work. Use the enthalpy data and just put this data, and this is the answer. So in a power plant, you have to find out the isentropic efficiency. So the isentropic efficiency of turbine will be H1 minus H2A. So that is the actual work upon the isentropic work. Okay, the isentropic will be H1 minus H2S. Apply the enthalpy of these state points, so it will be 91%. So same kind of question, a very big question. You are given different state points and all. The first, determine the fraction of steam extracted from the turbine. So like this fraction. Okay. So assume the fraction of steam blade at the state point 6. Now apply the energy balance. So doing the energy balance, we can do this. So this is the point 6. We are applying energy balance here. All energy is incoming. From here it's incoming. From here it's incoming. From here it's outgoing. Apply these. So mh2 plus 1 minus mh5 equals to 1 dot h6. So you can find out the value of m. Okay. We have given the table with the enthalpy data H2, H6. So H5 can be calculated from the pump work, as in our previous question also we calculated this. Okay. So apply this, the pump work. Okay, then H5 will be the enthalpy of state point at the curve and the pump work. So this will be the enthalpy at point 5, and this will be the your fraction of the quality of the steam. Now, which of the following is not related to the steam power plant? So the intercooler is not in steam power plant. In steam power plant, there is a boiler, there is a condenser, and there is an economizer. In Rankine cycle, heat addition takes place at constant pressure. Okay. And what is the use of economizer in a power plant? So it's used for preheating of feed water. Economizer is used to preheating of the feed water. So what is the effect of superheated steam in the Rankine cycle? So they increase the thermal efficiency. Okay, they increase the thermal efficiency, because if the steam is superheated, it means there will be high temperature. The work output will be more from the turbine. So they will increase the efficiency. Open feed water heater is direct contact heat exchanger. Open feed water heater is a direct contact heat exchanger. A steam power plant operates on Rankine cycle with reheating. The cycle is shown below. Okay. Which one is corresponding a high pressure turbine expansion? So the B, C to D is the high pressure turbine. The B to C, sorry, B to C is the high pressure turbine expansion. D to E is the low pressure turbine expansion. C to D is the reheating. So the correct answer is B. B to C is the high pressure turbine expansion. The TS diagram of a Rankine cycle is given below. And what are the process associated with 2 to 6? So here 2 to 6 is like we are extracting some heat, some also fraction of the steam. Okay, so the 2 to 6 is with connected to the open feed water heating. In the Rankine cycle, regeneration results in higher efficiency but low network output. Okay, if you are doing regeneration, then efficiency will be higher but the lower network output. The pinch point is difference between the temperature of flue gases and inlet of evaporator. So the temperature between of the flue gas and the inlet of evaporator. Exergy destroyed in the turbine is equal to the difference between the exergy delivered to the turbine by the working fluid and exergy delivered by the turbine to the shaft. So this is the exergy destroyed. Basically, so the delivered to the turbine by the working fluid. So working fluid is having some exergy, and we are also delivering some exergy in the form of energy. So that is delivered by the shaft. So difference of these will be the exergy destroyed. So that much amount of energy we are not able to use. In the diagram given below, the process 1 to 3 shows the actual expansion in a turbine, and process 1 to 2 is the isentropic expansion of from the boiler pressure to the condenser pressure. So what is the isentropic efficiency of the turbine? So it will be efficiency H1 minus H3 upon H1 minus H2. We have already covered it. Which one is the true for idle Brayton cycle? So it is commonly used topping cycle. Okay, and its efficiency depends on the pressure ratio and type of gas used. So these two are for the idle Brayton cycle. It's commonly used as topping cycle, and its efficiency depends on the pressure ratio and types of gas used. Now supplementary firing in HRSG. So it means that burning additional fuel in the exhaust of topping cycle and increase total power output. It is used for supplementary firing in HRSG. For a gas turbine, with maximum temperature T3 and minimum temperature T1, the optimum pressure ratio for maximum net work output is given by. So it is given by the T3 upon T1 to the power gamma upon 2 gamma minus 1. This is the optimum pressure ratio for maximum net work output. Okay, the important question. So optimum pressure ratio for net maximum work output is T3 upon T1, like maximum temperature to the minimum temperature of the cycle to the power gamma upon 2 gamma minus 1. So this is the complete derivation for this. The efficiency of topping and bottoming cycle of a combined cycle power plant are eta 1 and eta 2. Then the correct expression for the efficiency of combined cycle. So we know that combined cycle efficiency will be eta equals to eta 1 plus eta 2 minus eta 1 eta 2. Or we can write 1 minus eta 1, 1 minus eta 2. Both statements are same. So we have to find out the efficiencies. Okay. So the current efficiency 1 minus T minimum minus T maximum. So apply the formula and see the temperature. So it will 75%. And Brayton cycle efficiency 1 minus 1 upon Rp pressure ratio to the power gamma minus 1 upon gamma. So it will be 0.4. And the ratio of these two, Brayton to Carnot, will be 0.53. So this was the answer. Find the ratio of gas turbine efficiency to the Carnot cycle efficiency. Okay. So find both of them separately and find the ratio between two. So this is the given block diagram of gas turbine power plant. Okay, it shows combustion chamber, intercooler, reheater, and regenerator. So which are represented by the letters P, Q, R, and S. So P is representing the intercooler, and Q is the regenerator. Okay, here we are like using some high temperature of the exhaust for the turbine to reheat the input to the reheater, or you can say combustion chamber. Combustion chamber, or S is the reheater. By using a combined cycle gas turbine and steam power plant, specific fuel consumption can be decreased, efficiency can be increased, work output can be increased, and the waste heat from the gas turbine or topping cycle is routed to the steam turbine bottoming cycle, which generates extra power. Okay. Then a simple idle Brayton cycle with air as the working fluid is given. Okay. So we know that for the isentropic process, T2 upon T1 is equals to pressure ratio to the power gamma minus 1 upon gamma. It's a very strict thermodynamic formula. Apply this. P2 equal to P3 because this is the constant pressure line. Okay. P1 equal to P4 also constant pressure line. So apply this data. Now back work ratio, as we have already covered, the compressor work upon turbine work. Okay. So the compressor work will be H2 minus H1, and this is turbine work. Okay. So in this case, you have the temperature. So enthalpy will be Cp, T2 minus T1. Cp will cut out, and with only temperature, you can find the answer. It will be 40%. So it's quite a long question. Maybe we can see go through this later. So the efficiency of HRSG can be improved using. So we can do the multiple pressure steam generation. Okay, low pinch point temperature difference and low approach point temperature difference. In this, by using these three, we can improve the efficiency of. Identify the correct statements of figure 1 given below. So the process 1 to 2 in figure A and B shows wet and dry expansion respectively in the turbine of organic Rankine cycle. Okay, so process 1 to 2 is the wet and dry expansion, and process and the superheating is required for fluid in figure A for dry expansion in the turbine. Because if you see in figure A, this expansion is happening in the vapor plus liquid region. Okay, so if you want to dry expansion, then these points should be outside this curve. Okay, so we require superheating. So if we do superheating, then this point will shift to something here. Okay, and then we will come into the superheated vapor region. It will count as dry region. Okay, so the superheating is required for the fluid in A for dry expansion, and the process 1 to 2 A and B show wet and dry expansion. So this is the wet expansion. This is in the superheated vapor area. So it is a dry expansion respectively. So in Kalina cycles, phase change process are modified to reduce irreversibility. So we have phase change process are modified to reduce the irreversibility. In this case, we can also increase efficiency. So to improve the heat exchanger between a gas and a liquid stream in heat exchanger, it is decided to use fins select suitable option. So fins are generally attached on gas side as heat transfer coefficient on gas side is small. Okay. So as I think you have also seen in on the like motorbike engines. So on outside the engine, we are having a fin structure. Okay. So that this basically are using increasing the area. You can see this area has been increased. Okay. So there is more area. It means there will be more heat transfer. Okay. Because the heat transfer coefficient is low. So we want to increase the area so that that low coefficient can do more heat transfer with high area. That's why fins are generally attached on the gas side. So what is the correct statement regarding organic Rankine cycle? So to avoid liquid condensation during expansion, it requires dry expansion. Okay. Low temperature and renewable energy source can be used for vapor generation, and it can run without superheating of the working fluids. These are some statements regarding organic Rankine cycle. So which of the following statements are correct for displacement condensation subsystem DCSS? So A, B, C are correct. Okay, so basic solution fed to the absorber is a combination of lean solution of NH3 coming from separator and mixture coming out from the recuperator. And the basic solution
Hello,
is
sir.
needed. Yeah, hello.
Sir, in previous question, please.
Yeah.
Sir, in our assignment solution, it is written that option D is not correct, sir.
Okay.
Yes, sir.
Okay, so maybe I have to check that. If it is in the solution now, maybe that will be correct. Yeah. Maybe because I think this solution is quite old. I have to check this. Okay, slide number 100. So let me mark it. I will check and I will update the answer in this slide maybe. Okay. So statement regarding organic Rankine cycle, it can run without superheating of the working fluid. Okay. I have to check it. Yeah. So the trilateral flash cycle in shown figure 3, the correct options are so both A, C, and D. Expansion takes place within two-phase region. So yeah, this is the two-phase regions. Okay, here's the expansion. Then the working fluid has a low boiling point. Correct. And the substantial amount of heat is transferred to the working fluid in a subcooled condition. So here you can see
Sir, in this question also option D is not correct, sir.
in this question also.
Yes, sir.
Okay. So is this in your assignment? Same question was in your assignment?
Yes, yes, sir. In assignment, this question, same question is given, and the option D is not correct. They have provided the solutions. Option D is not correct, sir.
Okay. Okay, then I have to check it because maybe because these answers also from NPTEL team actually we have received from them only. Okay, I have to again go through it, I think. So question number, slide number 102 also. The previous one was 100, I think, yeah. 100 and 102. So now we are the question about the counter flow heat exchanger. Okay. So the LMTD formula is del T1 minus del T2 upon ln del T1 upon del T2. Okay. So find the terminal temperature differences. So this is the special case form. Okay. So this form can become 0 by 0. Okay. So you have to apply the L'Hospital rule. After applying L'Hospital rule, you can find that direct the LMTD is only delta T. Okay. So you don't have to like this is only for the concept, but if this is a special case occur like this, then delta LMTD will be directly the temperature difference. That will be the 50 in our case. Okay. As the temperature difference of two ends of the counter flow heat exchanger are same. Okay. This del T1 and del T2 are both same. So this del T will become the LMTD. This is the solution for it. But this is a special case, so you can remember this. That will be easy. The correct expression of NTU, net heat transfer unit in heat exchanger. So NTU is UA upon the minimum. So here you have to just apply the heat transfer formula, that is MCP, temperature difference. Okay. So you will get the data. So after that, since the heat transfer rate remains the same, because if we are using a heat exchanger, then heat transfer rate remains same. Okay. Just the fluids hot stream and there is a cold stream. So heat transfer rate is the same for both hot stream and cold stream. So you can apply this heat transfer to this stream, the cold stream. Okay. In this way, you can apply this data, put this Q as here. Okay. You have MCP and put this data, you can find the temperature. So in the previous problem, what is the LMTD of heat exchanger? So LMTD, you know, temperature difference of terminals upon ln del T1 upon del T2. Put the data, this is the answer. To identify the correct statements regarding the rotary generator. So it is used only for gas to gas heat exchange and it contains a storage matrix. Identify which of the following is true for regenerator with a rotary hood. It is used as an air preheater and it has a fixed matrix and fixed streams of gases. So correct statements regarding run around coil system. So it should be used only when the distance between the hot and cold stream is large. So if there is a very large distance, then we have all of the above actually. So it is suitable for heat recovery in air conditioning system. It consists of two heat exchangers and need extra auxiliary power. There is a system run around coil system. Okay. So in these three cases, we can use that. Okay, so can skip these some long questions because you have limited time. Okay. So you have to find out the NTU. So like we have different kinds of formula for NTU. Okay, as per the flow arrangement, we have NTU's formula. So try to like remember some pattern to remember this formula, or maybe sometime you can have these kind of tables in your exam also. You can use these kinds of table also. Okay. So recuperators are direct transfer types heat exchangers which fall into the category of indirect contact heat exchangers. Which of the following statements is or are correct for the recuperators? So for recuperators, there is no direct mixing of the two fluids because each fluid flows in separate fluid passage. Okay, there will be no direct mixing. It transfers continuously from the hot fluid to the cold fluid through the dividing wall. Some examples of recuperator are tubular, plate type, and the extended surface exchangers. So these are like about the recuperators. Regenerators are storage type exchangers falling into the category of indirect contact heat exchangers. Which of the following statements are correct? So basically the corresponding thermal energy is alternately stored and released by the matrix wall, compact surface area, okay? And the compact regenerator usually has a smaller volume and lower in weight than equivalent recuperator. These are the benefits of regenerators. Which conditions should be satisfied for hot and matching in pinch analysis? So a number of hot stream should be lesser than or equal to number of cold stream. Okay, and the heat capacity rate of the hot stream should be lesser than or equal to the heat capacity of cold stream. So heat pipes transport heat dominantly in one direction. So the axial thermal conductivity is very high in heat pipes compared to transversal thermal conductivity. Okay, so it's very high axial thermal conductivity, and dimension of pipe in axial direction is much higher compared to the dimension. So anyone can give any example of heat pipes? In which devices we are using heat pipes? Anyone? Alok? Any idea about heat pipes example? Like in which devices we are using heat pipes? Prashant? Okay. So basically we are using heat pipes in our laptops, okay, in our electronic devices where the space is limited. We are not having so much of space for the airflow and all, okay. And the design is also like this that the area which require the cooling is not near the vent, okay. So we can use the heat pipes. So by the heat pipes, suppose our in our laptops or computer, so there is a heat pipe is here, okay. So that will go near the vent. So here we can place a small fan, okay. But the point where we need cooling is here. In between, we are using heat pipes, okay. So they are having a very high axial thermal conductivity. So they will pass the heat to the outside. So in laptops, okay, in mobile, I think in mobile there are very different kinds of the systems are there, but basically in laptops and many small devices, we use heat pipes. So heat pipe acts as a passive heat transportation device. Okay, heat pipe does not need external power to pump the condensate back to the evaporator. Hence, it is a passive operating device. So it does not need external power. So it's a passive heat transportation device. Which of the following orientation of the heat pipe is preferred to attain maximum performance? So vertical with bottom evaporator and top condenser. So yeah, the pressure difference due to hydrostatic head assist pumping effect in moving the liquid from the condenser to evaporator. So the capillary pressure head must be greater than, so it will be sum of liquid pressure drop in the wick, vapor pressure drop, hydrostatic pressure head. How bend along the length of heat pipe impact functioning of the heat pipe? So bend in the flow path will result in additional pressure drop. We are having more bends and there will be more pressure drop, resulting in lower flow rate and power rating. So try to eliminate the bends. Which of the following are the features of vapor chamber? So it's 2D heat dissipation, because in heat pumps there was only 1D heat dissipation. Okay, it's similar working principle as heat pump and passively operating in nature. Unlike heat pump, vapor chamber dissipates heat in planar direction and has similar working principle as that of heat pipe. Which of the following generate power in electric generator? So the in thermoelectric generator, power is generated due to the temperature gradient at junction of two dissimilar metals, which results in an EMF due to Seebeck effect. Okay, so the temperature gradient is important. That can be that can use to generate a power. So I think I also gave an example about new improved design of cook stove, in which they are using this TEG thermoelectric generator. So basically they are using the temperature gradient that can be generated in a cook stove, and from this TEG they can charge a small battery, and from that battery they can use to light a bulb or to charge the mobile and to charge small devices. So in thermoelectric device, the thermoelectric elements are connected to each other in series according to electrical connection, in parallel according to thermal connection. So in the liquid mass flow rate in the heat pipe is found to be, you have given the liquid mass flow rate, calculate the axial power rating. HFG is given, so the heat transfer will be QM HFG. It will be 45 watt. Think some slides repeating. Yeah. So the thermoelectric generators are and thermoelectric refrigerator work according to the Seebeck effect and Peltier effect respectively. The thermoelectric generator works according to Seebeck effect, where temperature difference is converted to electrical energy. Okay. And on the other hand, the thermoelectric refrigerator works according to Peltier effect, where voltage difference or electric energy is applied to create temperature difference. So here we are applying the voltage and creating a temperature difference. On the other side, we are using the temperature difference to create the voltage. Figure of merit G for a TEG is a function of material properties. Okay, is depend on thermal conductivity, Seebeck coefficient, and electrical resistivity, which comes under the material properties. The G value is hard to increase as it is difficult to get material with low thermal conductivity and high electrical conductivity. If the Rp and Rn equal to like 1.5 and 1 ohm, okay. So this is the formula for semiconductors. RL equals to Rp plus Rn. So the external resistance will be 2.5 ohm, results maximum efficiency. The efficiency of MHD is limited by ionization potential of the gas, and below 2000 Kelvin the gas molecules become neutral. Because the gas ionization potential is critical for release of electrons, So the ionization is lost below a temperature of around 2000 Kelvin. Okay, so it should be around maybe 3000 Kelvins. As electrons combine with ions or to form a neutral molecule, which restricts the temperature gradient of operation. So is the formula for this calculation. Which of the followings are true? So at absolute zero temperature, Fermi energy is non-zero. Okay, and work function of the collector is lower compared to the work function of emitter. In a power plant with hot gas coming from combustor at 3000 Kelvin, one can use an MHD, a TPV, and TEG before using the gas in the steam generator. What should be the order? So the order should be MHD, TPV, and TEG, because MHD must be used first when the gas temperature is highest. Okay, because that it should be more than 2000 Kelvin. Since it loses its ionization potential below 2000 Kelvin. Thereafter, the TPV should be used as the emitter temperature function above 900 Kelvin. Then the TEG does not have any temperature restriction and can work across any temperature gradient, hence it should be used at the last stage. So this is also important whenever you are trying to implement any technology, so that first you have to understand the technology, like what are the conditions for the technology, and you have to understand the state points of your plant. So based on that, you can decide the technology and the location of technology at where it should be implemented. So the combined cycle efficiency will be 1 minus eta C equals to 1 minus eta 1, 1 minus eta 2. So you can find the efficiency with this formula. So COP of heat pump is always greater than 1, because it's 1 plus COP of refrigerator. So specific heat of heat pump depends on air volume and air charge requirement, cooling load, and heating requirement. Temperature is a water type heat pump and uses two compressors for its operation. Templifier. Templifier is a water type heat pump and uses two compressors, so that low pressure and high pressure compressor for its operation. For an air heat pump used for year-round air conditioning, what is the function of the four-way valve? So the four-way switch changes the route of refrigerant. So basically, it reverts the functioning of the evaporator and condenser. Okay, so that the indoor heat exchanger functions as evaporator in summer and condenser in winter for the refrigeration cycle. Similarly, the outdoor heat exchanger becomes the condenser in summer and evaporator in winter. For drying application, the most warm air is passed through the evaporator to reduce the temperature of warm air and to condense the water vapor and remove it from the moist air. Incinerators are categorized according to the state of waste that is being incinerated. Because there can be different kind of waste. So as per that, we have to categorize it. In the fume incinerator discussed in class, what is the gas that is used for the synthesis? It was and butane. We have given some data based on that we have to find the COP. So COP desired effect upon work input, so that will be 20.2. For the above heat pump, what is the work done by compressor? So we know the COP, we know the work, the heat added. So based on that, we can find the work input. So what are the mechanical storage systems? So the pumped hydroelectric systems and compressed air energy storage. What is the desired effect in heat pump system? So heat rejected at high temperature is the desired effect of a heat pump system. Now size of a heat pump depends on air volume and air charge requirement, cooling load, and heating requirement. In a winter heat pump, what can be used for the chilled air? So used in a water cooler, used to cool data centers and to run a and to refrigerate products in a dairy farm. Now, for an air heat pump used for year-round air conditioning, what is the function of the four-way valve? So we have already covered it, reversing the functioning of evaporator and condenser. So Templify unit can do the improve COP, and it's also can handle high temperature lift. So an incineration plant can be used for remove pollutants from gaseous waste, disposal of waste, and process heating. So for both these applications, it can be used. So in fume insulator, it was N-butane. So these numericals, you just apply the basic concepts. You can do these. So main objective of energy storage, to offset adverse effect of fluctuating demand, assure steady output from the existing plants and meet peak demand on short notice. What kind of turbine for pumped hydro? So it's Francis. Okay, because it can also act as a pump to pump liquid back up in off-peak hours, because we have to pump back the liquid during off-peak hours, so it can be used for both turbine as a pump. The compressed air entering to the reservoir has high pressure and low temperature. Because air pressure is high as it passes through the compressor, and temperature is low after it passes through the heat exchanger before entering the reservoir. So what kind of heat exchanger is used in CIS? It's regenerative. So energy storage can be found out by the MGH. So you know the stored energy, you know the M and G, so you can find out the H. So CS compress the air and stores energy in form of potential energy. On the other hand, flywheel stores energy in the form of kinetic energy. So flywheel store the form in kinetic energy and store energy in the potential energy. So the following what is the correct variation of the current is charging, storage, and discharging state of SMES. So it linearly increase, constant, and exponentially decrease. Okay. So T2 upon T1, use the basic formula. You can apply this. So the compressor efficiency is given, okay. So apply the formula for compressor efficiency. So in pumped hydro system, which is not a source of loss. So water addition due to rain. Because if water is adding due to rain, then it is not a loss, because it's automatically a natural phenomena. Why is the compressed air in storage system cool before storage? To reduce storage volume, because we are storing it. So we want to reduce the temperature, because high temperature requires more volume. In SMES, magnetic energy is converted into electrical energy, and magnetic energy can be stored indefinitely, and electrical resistance of the coil drops to 0. The flywheel energy storage is increased by locating more mass at the circumference, okay, and reducing friction loss and choosing material with high tensile strength. These are the three things that can be used to store more energy in the flywheel. So in this, I think recuperators uses waste heat from turbine. This was the reason that the Alabama CA is more energy efficient than the Huntov installation. So apply the flywheel formula that we have discussed. You can calculate the energy stored. So melting refers to the charging, and solidification refers to the discharging in thermal energy storage using PCM. Okay. So during discharging, concentration of electrolyte decreases, lead acid batteries, and bulky in size and self-discharge with time. These are features of the lead acid batteries. So as we are shifting towards hydrogen economy, so what are the challenges as hydrogen is a fuel? So it's high storage volume, okay, and flammability. Because I think 1 kg of hydrogen is equals to 11 meter cube. Okay, so very less energy density. So storage volume is very high and is highly flammable. Okay. End products of fuel cell are water and heat. So in fuel cell, end products are water and heat. This is the formula for voltage calculation in PEM fuel cell. So typical value of thickness of the catalyst layer in PEM fuel cell is 10 micrometer. What is the function of gas GDL in PEM fuel cell? So it distributes the reactants uniformly and connect the catalyst layer to the bipolar plate electrically. The distribution is very important because if distribution not uniformly, then the cell will not work properly and there will be low voltage from the cell and the efficiency will be low. So apply this formula, you can get the answer. Over the years, EROI values of oil is decreasing. We have discussed it here. And the matrix of energy does not consider time value of money. So ROI and payback period are not considering the time value of money. And LCOE and NPV is considering the time value of money. So for NPV for the viable industry in terms of economics, NPV should be greater than 0. So LCOE is useful for comparing competitiveness of different energy installation. It is also considering the time value of money, so we can easily compare different kind of energy installation. So EROI is energy out upon energy in. Input output analysis was developed by the Wesley Leontief. Okay. So I think we have discussed this numerical yesterday. We have to find out the average load, then generated energy and revenue. Now we have already calculated the revenue, energy and all. So now the amount of coal required per year based on the calculated energy. Okay. So you can find out the cost of coal per year. You have given the data. And net annual cash flow will be like this. The main thing is in this type of question, like be careful with the units. Okay, because they will be in megajoule, kilojoule, in crores, lakhs. Okay, so be careful with the units like kg and ton. Be careful with the units. So this is, I think we also covered. So just apply the formula for NPV. Like for first 2 years, it will be 30 lakhs. Then for 2 years, 45 lakhs. Then 75 lakhs. Then salvage value. Okay, then minus the installation cost. So you can get the NPV. So it is the saving per year. So what is the drawback of payback period as a metric of energy economics? So it does not consider the time value of money. LCOE, comparing competitiveness of different energy installation. You know this. Okay. And the EORI is 90 to ratio 1 in 50s and around 5 ratio 1 today. What are the primary reasons? So wells are require deeper exploration, and oil fields are getting smaller, and rigs have become complex and expensive. So basically, we need to invest more energy to uh, tap tap out the oil. So it means that ERO is reducing. The input output analysis, Wesley Leontief. Okay, guys. So we have covered just a moment. Okay, we have covered like very fast all assignment questions, and I think some we directly passed and some we discussed. So I hope today's session was also useful to you, and those who are like going to watch it online, maybe it will be useful for you to revise all the assignment questions, or maybe these questions will help you in your upcoming exams. So I hope I helped you a lot in these our 30 classes. So I tried my best. So all the best for your exam. I hope you will do well, and please like do the best in your exam and get a very good grade. Okay. So if anyone want to say anything, floor is open. I think we have already discussed with Prashant. Alok, are you there?
Sir.
Yeah. Thank you, Prashant, for joining. I think it was great discussion with you. So I
Thank
hope
you.
you will use. I hope you will use your knowledge and do very best for our country. Okay. And yeah.
Sure, sir. I will try definitely, sir.
Yeah. Thank you.
Thank you,
Alok,
sir.
do you want to also say anything about the course and all? Okay, I think Alok is on hold. So okay, once again, thank you for joining this session. Okay, thank you for last 13 classes. I enjoyed very much with you all guys, and thank you for joining, and all the best for exam. Thank you.
Thank you, sir. Thank you.
Thank you. So with this, I am ending this session. Thank you all. So you will get the recordings and the PPT from the NPTEL team very soon. All the best and thank you.
Thank you, sir.
Bye bye.
Bye.